This set of videos brings us the last two tests. We start out with the definition though. A series sigma a sub n is called absolutely convergent if the series of absolute values sigma absolute value a sub n is convergent. For example, the sum as I goes from 1 to infinity of -1 to the n divided by n squared is convergent. We know that by the alternating series test. It's also the case that the sum as I goes from 1 to infinity of 1 over n squared is convergent because it's a p-series with p greater than 1. So we say that the sum as I goes from 1 to infinity of -1 to the n over n squared is absolutely convergent. That is, its convergence doesn't rest solely on the fact that it was an alternating series, and if we drop the -1 and have the absolute value of the terms, we still have convergence. By contrast, if we consider the sum as I goes from 1 to infinity of -1 to the n over n, we know that that series is convergent by the alternating series test. It's actually called the alternating harmonic series. Not really the point right now, but hey, it's information. But the sum as I goes from 1 to infinity of 1 over n is divergent because it's a p-series with p less than or equal to 1. So when we have the absolute values of the terms, we lose the convergence. We would then say that the sum as I goes from 1 to infinity of -1 to the n over n is conditionally convergent. It's convergent only under the condition that it's alternating. We have a theorem that when you see it, you're going to go, well, duh, but we're going to write it down anyway. If a series sigma a sub n is absolutely convergent, then it is convergent. And one of the things I learned in college is duh is not a proof. And so there is actually a proof for this statement. A sub n plus the absolute value of a sub n is basically either 0 or 2 times the absolute value of a sub n. Depends on whether a sub n is positive or negative. But it's true that that sum, a sub n plus the absolute value of a sub n, is between 0 and 2 times the absolute value of a sub n inclusive. If we have that sigma a sub n is absolutely convergent, then that means that sigma of absolute value a sub n is convergent by definition, which would mean that sigma 2 times the absolute value of a sub n is convergent because a constant factor does not affect convergence. Then because a sub n plus the absolute value of a sub n is less than or equal to 2 times the absolute value of a sub n, by the comparison test, the sum of a sub n plus the absolute value of a sub n is convergent. So then what we have is that sigma a sub n plus the absolute value of a sub n is convergent. We have that sigma absolute value of a sub n is convergent. And so when I subtract them, I get a series that's convergent. But as it turns out, if I take sigma a sub n plus absolute value a sub n minus sigma absolute value of a sub n, the absolute value of a sub n's subtract out, and I may end up with sigma a sub n. And now I have that sigma a sub n is equal to the difference of two converging series, which means that sigma a sub n is convergent. Now, to look at the forest past the trees here, we started with a statement that sigma a sub n is absolutely convergent, which meant that sigma absolute value a sub n is convergent, and then we got to the conclusion that sigma a sub n was convergent, and that's irrespective of the absolute values.